All right, so one thing that I want to talk about briefly is the energy that's stored on a capacitor, regardless of how you would find its capacitance. So when we look at a capacitor, we can look at the charge that we're able to store on the capacitor as a function of the velocity. And since C is Q over V, these are clearly related to a graph. And what ends up happening is that the first charge that you store is essentially free. It takes no push because there's nothing on the plate to repel back against the motion of charge onto the plate. Remember, we're trying to move charges from, say, a battery onto a plate, and the battery is initially nicely charged and the plates are empty. So there's no reason that a positive charge wouldn't want to just go onto that plate. But once we already have a positive charge on that plate, and a negative charge, by the way, on this plate over here, because this will repel positive charge away. Remember, these are all conductors, so as soon as there's electric field on something, it moves. The charge moves. Once we put a charge on here, it's now going to take more effort to get the next charge on. Now, this could be, say, a 9-volt battery. That first one took 0 volts. The second one's going to take a little bit more than 0 volts, but certainly not 9 volts. And this increases then linearly. So every charge we add makes it harder to get another charge onto the plates. So we end up getting a graph like this. What that means is that the capacitance, first of all, is the slope of that line. So if you have a capacitance that's really great, it would look maybe like this, where you have a very large capacitance because the results show you get a lot of charge on there for not a lot of push. On the other hand, if you had one that looked more like this, that would be a smaller capacitor or capacitance than the other ones. Now, how can we use this to help us understand how much energy is involved? Well, let's think about what energy is. Energy is joules. And when we look at charge is measured in coulombs. Volts is measured as joules per coulomb. So it stands to reason that if we multiply those two things together, we're going to get joules, because the coulombs will cancel out. And that's exactly what we're going to do, except we can't just multiply them by each other because it is not a constant thing. The voltage is not constant. The charge is not constant at every voltage, nor is the voltage constant at any charge. What's going on is they're increasing mutually. So what we have to do is we have to actually, so the amount of potential energy stored on a capacitor is actually related to the integral of, we'll do Q dV. Okay, it really doesn't matter which way you go, but this maybe makes a more logical sense, especially looking at the way that I graphed it. So what I would do is I would rearrange Q, and I would say that Q is equal to V times C. So now I plug that in here, and I have V times C dV, and then we get, integrate V, I end up getting 1/2 V squared times C, because C is a constant. It's the capacitance. You can see it's a straight line. Okay? So this is how much energy we would store on the capacitor. There are other ways to write this. I could instead, I could say, well, C is equal to Q over V, right? So if I plug that in here, I get 1/2 Q times V. Or I could say, well, V is equal to Q over C, and that would give me 1/2 Q squared over C. Okay? So these are the three ways that you would write the amount of energy. Hopefully this makes sense. This was a very brief, basic introduction, but that's all that I'm really going to do for this one.